Hi, I'm Lunas, and if you've been wondering how Savage Attacker math works out in Baldur's Gate 3 or in DnD 5e, this is the PowerPoint presentation or video just for you. I've been working on this for a few hours and I have some interesting math to show you. So what is Savage Attacker? Savage Attacker is a feat in DnD 5e and in Baldur's Gate 3, where when making melee weapon attacks, damage dice are rolled twice and the highest result is used. This is basically an advantage for melee weapon damage, and there are three possible interpretations for this. Interpretation number one: you roll every die individually twice and take the highest one. For example, if you have 2d6 plus 1d4, you roll each d6 twice and take the highest one. So if you roll a 2 and a 5 for one, you take the 5. If you roll a 6 and a 1 for the next one, you take the 6, and for the d4 you also take the highest one. In this example, this would yield a total of 14, while only the first roll would be 10 and only the second roll would be 9. The second interpretation is that you don't reroll individually, but in pools. So you take the 2d6, you roll them once, and you roll them another time, and you take the highest of these results. And for the d4, you do the same thing, but you roll it twice and take the highest of the d4. In this case, this would yield a total of 11. And the third interpretation is that everything is rolled together, and you just take the highest result. So you take 2d6 and 1d4, roll them all, add them together, roll them a second time, add them together, and you take the highest result. It must be mentioned that in DnD 5e this is only allowed once per turn, while in Baldur's Gate 3 it's just on every attack you do. So in Baldur's Gate 3 the feat is stronger than in DnD 5e. Also, it's unclear which of these interpretations is true, because Baldur's Gate 3 does not communicate it clearly. Because the feat description says, you roll it twice and take the highest result. This is also what the DnD 5e player's handbook says. But in the combat log, it looks more like you have some pools that are rerolled together, like 2d6 are rolled together and rerolled, and the 1d4, for example, through fire damage that you get from dipping, is rerolled individually. And then you have the Baldur's Gate 3 wiki, which confidently states that every single die is rerolled. So we have the first interpretation, which yielded the highest result. But this is also the most tedious at the table, so in DnD 5e I recommend that you use single pool rerolls, but they are, mechanically speaking, worse. So let's do the math for all these options, because, well, if there's no clarity, I just gotta do it all. Individual dice is the simplest one, and if the wiki is to be trusted, which I'm rather confident in, the Baldur's Gate 3 wiki is very reliable. So, how do individual rerolls work? We have a blue die and a purple die here, which represent the two rolls, and in this table we have the results that are actually the outcome. So if you roll a 1 on this and a 1 on this, then the result is a 1. If you rolled a 4 here and a 1 here, the result is a 4. If you rolled a 1 here and a 4 here, the result is also a 4. As you can already see, the 1 only occurs once in this entire table, while the 4 occurs 7 times. Also, another thing to note, and this will be a pattern throughout the video, 75% of results are above single roll average. So usually for d4, the average is 2.5. and only a quarter of the results is below that, while 3/4 is above it. This is also true for other dice, or, well, at least even dice, where if we were to look at something like a d7, which is rather rare, it's even more than 75%, which is at least average. If we are strictly looking for above average, it's a bit less than 75%. But the core of this comparison of the analysis is to find out whether Savage Attacker is better, or how much better Savage Attacker just is compared to average. I think, well, if it's at least average, I'm satisfied. No, I'm not satisfied, it's the cost of feat. Well, I'm rambling. Let's just continue. So, calculating the average damage. Well, we can look at each of these entries for the threes and we can just count them. Like there's always 5 threes or 3 twos or 1 1. Or we just take the number, multiply it by 2 and subtract the one overlapping number. This way we also notice that the 1 becomes almost, well, that the 4 becomes almost twice as likely while 1 almost never occurs. And here is that in a formula. So we just round up all the weights and the numbers, like 7 times 4, 5 times 3, and so on, and divide it all by 16 because we have 16 spaces. And we get our average damage of 3.125 for a 4-sided die. This can be formalized by doing some more complicated math. I won't bore you with the details on that. If you want to take a look at it, you can pause. First comparison, the average damage without Savage Attacker. It's always half the die plus a half. So for a 4-sided die, we have 2.5, for a 6-sided die, 3.5, for an 8-sided die, 4.5, and so on. With Savage Attacker, this formula arises from the calculations we did here. Or that I did here and I. Yes. So, it's a bit more complicated, but you don't have to do it yourself. I have a comprehensive comparison for you right here. And as you can see, the absolute difference that Savage Attacker yields increases with the size of a die. So with the D20, it's like comparable to advantage on ability checks and so on, yields an absolute difference of about 3.325. Well, not just about, it's exactly that in that case. So we now know exactly what the average improvement through Savage Attacker is. One thing I think is very interesting to note is that for the D12, the increase is almost 2. So Savage Attacker yields a damage increase of 2, which also equals like a fighting style for a one-handed weapon when not when yielding only one one-handed weapon. I think it's for daggers, short swords, and the like. And you can think for yourself whether you think that's worth it for a feat already. But also remember that in many cases, in Baldur's Gate 3, you will have multiple other damage sources that also profit from Savage Attacker, like dipping in fire, or bonus damage through elemental weapon, or also the bonus psychic damage from the strange conduit ring, and so on and so on. So, let's get to homogeneous pools. This is the case that the combat log lays near, so 2d6 are rerolled individually, are rerolled together, and the 1d4 is rerolled alone. Because it's getting quite cramped when we are using actual dice, now let's imagine we roll 3 2-sided dice, or well, coins labeled with 1 and 2 instead of heads and tails. We can represent this in 2 different ways. Here are all the combinations of the first 3 rolls rolled together, and here are all the possible combinations for the second 3 rolls also together. We can see that the 3 also only occurs once, the minimum result, and the 6 occurs rather frequently. Twice as frequently as, almost twice as frequently as usual. And if you are very perceptive or alert to Pascal's triangles, you can see that the weights for the 3 and the 4 and the 5 and the 6, in this case, are one of the lines in Pascal's triangle. We can also observe that, also in this case, 75% of results exceed non-Savage Attacker average. This is also true for cases where the average is between, where the average is exactly on point, like before. More than 75% of rolls are at least average. In this case, we are looking at 2d3. 3-sided dice are also exceedingly rare. I think in Baldur's Gate 3, no odd dice occur. But this case is also one that occurs when rolling 2d6, where the average is 7. Here you can also observe a number series which does not occur in Pascal's triangle, but we will get to that later. So, how do we calculate the weights in this case? I have two methods planned out. For one, of course, we can just count the 5s, count the 6s, count the 4s, count the 3s, and so on, and just multiply it with the number to calculate the average later on. Or what we can also do is we can sum up the weights of the previous entries, like these weights right here, or the number of rows and columns that this occurs. We can square that, and we can square that with the sum of weights up until this point. So we subtract the smaller square from the larger square, and only this remains. Another thing we can do is we can just take the weight for the 5 and multiply it with the sum of the weights for all the results before 5. In this case, it would be a weight of 2 for 5, because well, it occupies 2 rows and 2 columns each. We can square that once for this, and then we can add it twice multiplied with the sum of weights before, like 6. So, as teased before, for two-sided dice, the weights can be calculated using Pascal's triangle, or read from Pascal's triangle. I have written it down here so that the dice sums are noted above, and Pascal's triangle is a bit skewed here below, but you will notice it still has all its properties. Like these two summed together will form the number below, and this is also the case for all the other entries here. Like 15 is the sum of 10 and 5, 4 is the sum of 1 and 3. So like one number is the sum of the left upmost next 2 digits. That was a weird formulation. Each number is the sum of the 2 digits in the row above that are left to its own space. So, there's more. You can do Pascal's triangle for larger dice as well. In this case, for the d4. You start with a 4 once, because like if you were on d4, everything is just as likely. For 2d4, it shifts a bit. If you play Settlers of Catan, you might be familiar with the dot notation on the numbers. And here the property also remains that for any number, you then add together 4 consecutive numbers of the row above. And to find the weight of any given sum, like if, for example, I'm asking myself, what's the likelihood of rolling a 12 using 5d4, then I can just look at 5d4 and the sum of 12, and we have a weight of 155 here, which we can then use to calculate the average later on. Here are also the first few rows of t6 and t8. Like if this is t4, then the classic Pascal's triangle is t2. This also works for 6-sided dice, 8-sided dice. It works for any die, really. And here's how we find the weights using this method. I have found these triangles referred to as Pascal de Moivre triangles. Do correct me. In a study that I've read from 2012. That study is also where I found the second method of calculating the weights. It's a bit complicated, so I won't get into it too much. But you can formulate a few vectors, like if you have 3d6, you can build a few vectors that contain, that have 6 entries, which sum up to the number of dice used, and represent the individual results of the dice. Like if you're looking at this example for 3d6, for example, if we are looking for sum 8, here are the vectors that we need. It's like, yeah, we can get a 8 by 1 plus 1 plus 6. This is the 6th entry, this is the first entry. We can get it by 1 plus 2 plus 5, and so on. And by adding these together, using some factorials and, well, a bit of math, we can also get to the weight. Only the means of getting to these vectors is a bit tedious, but it's a more mathy way of figuring those out. And these vectors are like all unique vectors of the possibilities of summing up to 8. 2 times 1 plus 6 is 8. 1 plus 2 plus 5 is 8. 1 plus 3 plus 4 is 8. 2 times 2 plus 1 times 4 is also 8. And 1 times 2 plus 2 times 3 is also 8. So, you surely remember the ways to calculate with the sum of the weights times the weight times 2 for these two parts and the weight squared for this part, or the large square minus the smaller square. We can express it like this, with this expression referring back to either this formula or this method. This is the larger square, this is the smaller square, and this is the expression for the second method on the right side here. I, at one point, had everything filled in from the other formulas as well, but that was very disorganized, so I left it out here. So let's look at a few dice pools in comparison, just to build some intuition for how good it really is to reroll in dice pools. If we are looking at the singular d12, we see that with Savage Attacker in orange, the probabilities only go up. This is not the case for 2d6, but traditionally for 2d6, it's like peaked in the middle right here. If you play Settlers of Catan, you know this may be, well, probably, at least if you're a bit in depth about the mechanics, that the 7 is the most likely outcome. With Savage Attacker, this whole distribution is shifted to the right a bit, and the higher results are accentuated, while the lower results are, well, decreased. The average result is about the same. This is a pattern that can be recognized in almost all of these distributions. And for 3d4, just to get another comparison in, we see the same thing. Lower results are way less likely with Savage Attacker, and higher results are more likely. This can also more nicely be seen in this smoother distribution for 10d6. But also note that even if it makes the highest results far more likely, they are still very unlikely with Savage Attacker when rerolling pools. So formulas for averages. Even though the weights formulas, even for simple weights, is quite difficult, because the simple average, the simple distribution is symmetrical, like it's always mirrored at some point. The average is quite easily determined. This is not the case for Savage Attacker, because the distributions are not symmetrical. But this is the formula nonetheless. It's basically just iterating over every possible result and multiplying this result with the weight for that result, given that it's adjusted for Savage Attacker. So like one of these formulas, which refers to these methodologies. One example, with the weights already calculated to make it more comprehensible. When rolling 2d4, the normal average is 5, and with Savage Attacker is 5.891. Here's a comprehensive comparison of, well, basically everything you'd ever need if you wanted to roll such homogenous dice pools. If you're considering sneak attack for Savage Attacker, then maybe you run out of this table at some point. But one important thing to note, well, great axes outperform great swords is one important thing to note, like 2d6 with Savage Attacker in this methodology is less than a great axe can offer. Even if the base intuition with Savage Attackers that more dice are more good, plainly put. Observation number 2, which I alluded to earlier, the relative improvement diminishes with more dice. So this is for the sneak attack and smite enjoyers out there. More dice, if rerolled together, aren't that much better with Savage Attacker. Like if you're rolling 2d8 already, then you might not be, or 2d6 already, you might not be that happy with 3 more damage. But for singular dice, like for 1d6, an improvement of 1 is quite hefty. And this is represented in relative improvement, like plus 8.7%. Is not that fascinating, especially when compared with something like Great Weapon Master. Although I would note at this point that Great Weapon Master in these cases is also overrated. Because when rolling many individual dice, like, well, Great Weapon Master also Great Weapon Fighting Wand. Great Weapon Master. I meant to refer to the feat, not the fighting style. 10 damage is also not that much when comparing it with 10d8 smite damage, for example. And plus 10 damage does not scale with critical hits. Savage Attacker does. So, heterogeneous pools. What if we put all the 2d6s and all the 5d4s in one pool and reroll them together? How's the math working out for that one? Well, let's just look at one example. For 1d2 plus 1d4, we can still use the same methodologies to calculate it, like the two squares subtracted from another, or the sum of the weights before times the weight times 2 and the weight squared. And we can get the weights for all the different results. Like here we have a weight of 1 for the 2, a weight of 2 for 3, a weight of 2 for 4, a weight of 2 for 5, and a weight of 1 for 6. We can also get these weights by combining multiple, well, not combining, by making a mixed triangle. Mixed Pascal de Moivre triangles, excuse my pronunciation. So, yeah. We start with 1d4, add another 1d4 to it in the classic sense that we always look at 4 entries above. And then, when we add a d6 to the mix, we look at the 6 entries above. Like for this 15, this is the sum of these 6 numbers. And for this 76, when we add another d6 to it, we also look at the next 6 entries above. And like before, if we want to look at the weight for a given number, we can just look at the column for that sum. Like 2d4 plus 2d6, the weight to get 10 is 62. And this is that in text. So, the ways to calculate you should be familiar with by now. This is just a bit of adjusted notation to get the pools in here correctly, because we don't have the homogeneity anymore, so we can't just put n and x in there. But the pools will do the work. Also note that this x refers to the total number of dice. So, formulas for averages. We still have a very simple average for non-Savage Attacker, which just, in this case, we just iterate over the different homogeneous dice pools within the heterogeneous dice pool. So if we have 2d6 and 2d4, we build the average for 2d6 and add it to the average of the 2d4. And here we are doing some similar shenanigans. It just looks more complicated. Like for this denominator, we are also just iterating over every die, homogeneous die pool we have in the heterogeneous dice pool. And the same for the totals. So like down here, if we have 2d6, we take the 6 powered by 4 and the 4 powered by 4, and we have a denominator. As an example for 1d2 plus 1d4, we see here where we just add these two together. That's 1.5 plus 2.5 equals 4. And in this case, we have the denominator of 64, which is 2 to the power of 2 is 4, and 4 to the power of 2 is 16 multiplied with each other, like noted here, yielding 64. And then we have the weights of all of the different entries, which we can count or calculate, multiplied with the given result, and have 4.375 as the average for Savage Attacker. I do not have any comprehensive comparisons for this because it's quite complicated. Because, well, there's like many things to compare. Like, what do you want to compare 2d6 plus 1d4 versus 1d12 plus 2d8? I found it difficult to decide what would be useful information in that case. So, we are done with the math. Congratulations for making it this far. And now to a practical example comparison. Looking at the Suso Greatsword, it was probably dipped in fire, and through elemental weapon, it gets another 1d4 cold damage. Given the three interpretations from earlier, the individual rerolls, homogeneous rerolls, and heterogeneous rerolls, we can calculate the different expected average damage. Without Savage Attacker, we just add the averages for each die together, plus the base damage of 9, from these plus 7 and plus 2 acid damage for 21 total damage. This is also basically just the average between the two values here. When we're rolling individually, we can go back to the formulas we had in the first part of the video about individual rerolls, and we just add all of those together, giving us a result of 24.2 roundabout. So it's like plus 3 damage, free damage, if you will, when using Savage Attacker. If we use the homogeneous rerolls that are implied by the combat log, we don't have as big of an improvement, just 23.625. And with heterogeneous rerolls, like the ones that are implied in the feat descriptions, both in the player's handbook and in the game itself, we have an even lesser improvement of the damage. So if you want a strong Savage Attacker, request individual rerolls, and if you want to play efficiently at a table, you basically have to use heterogeneous rerolls. So, well, general conclusions. Savage Attacker is most effective on large dice, which Savage Attacker damage is at least non-Savage Attacker average damage more than 75% of the time. Savage Attacker almost doubles the chance of a max roll, and Savage Attacker makes the min roll almost impossible. I also want to give a shout out to Polynomial Triangles Revisited by Nureddin Farsi. Also, excuse my pronunciation, do correct me if I'm wrong. This study from 2012 helped me with finding the formula for homogeneous and heterogeneous dice pools. And, well, it was the first paper that I was able to find on wider Pascal's triangles, and that's also where I found Pascal de Moivre, triangles. So, and I have another confession to make. Math won against me when it comes to heterogeneous dice pools. Because I had this nice formula planned out to show to you, where I adapted the formula from the study to also encompass heterogeneous dice pools. But I won't bore you with the details. I think you may want to look at it if you accept my coming challenge. Like, here are some example vectors if we add together 2d4 and 2d6. Like, my idea was to restrain the vectors in another way so that, well, if you have 2d4, 2 of the numbers must be in the first 4, and the 2d6 can be anywhere. And then, by the same method, we can get different vectors to represent the different possibilities of getting to any given sum. So like in this case, to get to 16, we can do 4 times 4, because like 2d4 and 2d6 are giving that, but we can't just get 3 times 5 plus 1, which would be 16, but no, the 2d4 don't allow for that. We only have 2 dice that can even roll a 5, so this can't be a 3. This is the constraint that I tried to express with this one. And also, we need to count a bit differently, which you may see in this expression, which I also tried to write down like this, but it's quite janky. I got it to work for a few niche cases, but often with more dice it fell apart. So this definition isn't quite right, even though this calculation does work in this case because I made it retrofit to give that result, which also happened to make it work for a few heterogeneous dice pools, but well, I wanted to work for all of them, not just a few. So I challenge you all to find out how this formula or definition must be adapted to work. I have given up for now. There's some related code that I've linked in the description, and I've also linked the study that helped me formulate the formula for homogeneous dice pools down below. So I hope to hear some smart suggestions, and I wish you a nice evening. Have a nice day.